So, hello everybody, thank you for joining once again, and we'll start off with the second one of these little talks, which is really to do with what's everything made of. You look round and you see, I can see here all sorts of things, fabric hanging on the wall, a cork board, and more fabric on the floor, wooden floor, sort of plaster. Well, what's it all made out of? Is every different substance something completely different and unique in itself? Or are they all actually mixtures of a smaller number of fundamental things? I mean, a bit like you can make an awful lot of different things out of egg, flour, and fat, depending on what proportions you put them in. So are things basically different mixtures or different materials, different mixtures of a smaller number of fundamentals? Well, this is something that obviously occupied mankind right from the word go, and intriguingly, it turns out that in many parts of the world, a fairly similar lineup of basic elements emerged. Probably all of you have heard of the earth, air, fire, and water lineup, which the dear old Greeks came up with. But apparently, effectively, so did the Japanese and the Chinese and many Indian civilizations as well. Some of them had one or two more. Some of them rather cleverly had void or nothing as one of theirs, and that's pretty smart. But basically, it was a common feeling that everything is actually made up out of a smaller number of elements. That was one early view about the makeup of things. And the other was, wait for it, yes, the Greeks again, Democritus in 400 BC, sort of was wondering, can you just keep cutting something in half and in half and in half and in half? Could you just keep going forever and ever and ever and ever? Or would you eventually get to something that was as small as you could get for that particular substance? Is there a limit to how much you can go on dividing something? And he thought somehow it seems reasonable that there is such a limit, that everything eventually you get down to little atoms of the substance, and that's as small as you can go. So he had this thought, again, they're quite smart, I think. He was sort of ruminating and thought, well, because lots of things that you see in the world sort of decay. I mean, all trees and things collapse and rot, plant life, animals, they all rot and decay, even stones sort of weather away and disappear. And yet, new trees appear, new things appear, which suggests that when something's decayed, there's something left which doesn't decay. It may have fallen to pieces, but the tiny little pieces don't decay, and they can come together again somehow cleverly to make something new. So that was his input to the system, that everything is made out of little tiny atoms which themselves don't disappear. They might come apart, but they are still around to be made into something new. So that was where we were 400 BC, and where we continue to be for a good, well, pretty much 2,000 years, actually. And after the 1600s, sort of beginning of the scientific revolution, as we talked about last time, in the 1700s, really, people started getting more serious about thinking, well, what actually is everything made out of? And are there some materials that seem to be sort of irreducible, and are others made of others that we can actually do experiments with? So experiments started. I suppose alchemists had, by their failure, effectively pretty much established that you can't actually make gold out of anything else. Gold seems to be sort of elemental. You either have it or you don't, but you can't stick two things together and make gold out of it. And in fact, quite a lot of metals seem to be like that a pure silver, you can't make it out of anything, you just have it. It might come out of rocks, but you can't put two things together and make it. So metals, quite a lot of metals, looked as though they might be elemental. But what about other things? Well, now this is where people started quite laborious experiments of mixing things together. And I suppose, you know, you sort of, if you get two lots of material, two things like ground up, I don't know, sulfur and ground up something else, and you heat them up, and eventually you find that you get something else, and you say you get something different, but with a little bit of this one left. And then after repeating these sort of experiments, you become to establish that, okay, this amount of that stuff always makes a compound with that amount of this stuff. There seems to be a fixed ratio of them, and by doing lots of careful measurements of how much is left, and if you mix this with something else and then see how much of that one is left and what comes out, and weigh them and carefully tinker about with them, you start beginning to establish what things are elements and what things are compounds. And this was all happening. Share the screen, let's have that. These were the sort of some of the key names in this period. We have Carl Shady and Sir Humphrey Davy were quite good element inventors. But really, I think the two key people, and perhaps the most key, is Monsieur de Lavoisier, who was really the sort of founder of modern chemistry. He was very assiduous with his careful experiments. He identified quite a lot of elements, and he actually was the first person to develop what he called a list of elements, and he had about 50. Now, some of them we now know aren't elemental, and some of them were odd things like heat and light and stuff like that. But he had the idea of trying to get a list of things that you couldn't make with anything else. And he also discovered...
Andrew?
Yes.
Andrew, I'm very sorry to interrupt you. Could you let Flo into the room?
Oh, yes. Thank you. Right. Sorry. Yes, I hope you haven't been waiting too long. Sorry, Flo, about that. And yeah. So he discovered that if you did your experiments in a bell jar so that any gases that came or went were captured, you actually never changed the overall weight of what was in there, even if what ended up looking quite different from what you started with, and maybe, as I say, some gases came out or went in, but the mass never changed. The conservation of mass, he said. You don't change or destroy or create anything, you just transform them. Rather similar, you may think, to the sort of description of the conservation of energy that we had last time. And he, therefore, and he also got a much more systematic way of naming things and compounds. Instead of sort of spirit of Venus or something, he thought, well, okay, if it's made out of carbon and oxygen, it's called carbon oxide or something like that. So he invented all of that and really got the whole thing going. John Dalton put the final little bit of icing on the cake by saying that, okay, he combined these ideas with the atomic theory, whereas this was beginning to become popular, that things were ultimately made out of corpuscles. And he, again, from all the observations that people had made, came to see that, I don't know, supposing one takes, you know, something like sodium and chlorine, you know, I mean, that's not a very good example, but very much one could, from all these careful bits of data, begin to establish that when you made sodium chloride, which is basically salt, it always had one atom of one part of this to one part of that. In fact, nearly all compounds that were made by heating things up and mixing two things together and ending up with something that was rather different from both of them seem to have integer numbers, that they were in simple ratios. It was either one of this to two of those, or two of those to three of those. It seemed as though what was happening was that a corpuscle of salt consisted of an atom of sodium and an atom of chlorine. That seemed to be how it worked. Some of them might have two of them, but that was the sort of principle. And he also established, and quite how you distinguish from these things, I mean, one knows in general terms that it must be very complicated, because of course all of these things also, each atom has a slightly different weight. And so you can't just say that, okay, this is always twice as heavy as that, or they're the same weights, because chlorine atoms and sodium atoms actually are different. And that was gradually worked out too. They were able to determine not only the sort of ratios that things joined in, but what the masses of the individual things were. So this was a laborious and lengthy effort, gradually going on, but as time wore on through the 1700s, more of these elements were identified, and continuing on into the 1800s, yet more were identified, and a picture was built up of basically a relatively small number of elements, you know, about 100 or less, from which everything else was made by combinations of these atoms into what by then began to be called molecules, which is a corpuscle of different elements in it. The final sort of piece of the jigsaw we're going to look at today was then really, this was where the final chap on that list that you've just seen, Dimitri Mendeleev, comes in, as it began to be realized that if you put your material, the elements that you found, in order of mass. So in other words, you started off with the one that was lightest, which was hydrogen, and then you had the next one, and then the next one, and you went on just sort of if you like, putting the elements in the order of mass, of heaviness. You began to notice a sort of pattern emerge, that you started off with something that was a little bit metallic, and then you got something that was inert, and then you got something that was metallic again, and then something that was a bit more metallic, and then as you trundled on, you got to things that weren't metals, and then you got to something that was inert and didn't react at all. Then you got some more metals, then you got some more non-metals as you went up, and then you got another thing which didn't react at all. And Mendeleev realized that if you put them in a nice little diagram, you got something which seemed to make really quite a lot of sense. Now I shall share screen again, and I came up with this famous periodic table of the elements, which he organized it like this, which then revealed sort of patterns in these elements. There were some that were very energetic, some that were very reactive and liked to form compounds, others that weren't reactive and didn't like to form compounds. Now then, annotate, here we are, annotate, spotlight, let's have a spotlight. Yes, can you all see that funny little red thing tootling around? Has that appeared on your screens? Anybody into thumbs up? Can you see a little red blob? Yes, oh good, right, okay. So he discovered that, okay, if you order them like this, then everything down here is a metal and is an extremely reactive metal. As you trundle over to here, indicated by colors on this thing, these are not metallic. These are the most reactive non-metals. They get less reactive as you go in this way. The metals get less reactive as you go in this way. These are completely inert gases. They don't react with anything. They just sit on their own. Why? Nobody knows at this time. Now you will find out, or you lucky people, yes, all will be revealed as to why they do, but at this stage it was just how things were. And also for the metals, it seemed that the heavier they got, the more reactive they got. Cesium and francium are perfectly evil compared to lithium, whereas with the non-metals, it's the other way around. Fluorine is fearsomely reactive, and they get less reactive as you get down here. Why? Don't know. The period isn't the same either. To start with, these two light ones, it seems to start repeating straight after 2. But now you get 2 more cases where it's after 8 more. And then you get a case where it's 18 before you start repeating the pattern. And then you can see this little bit down here, these purples and pinks actually slot into those gaps there, meaning that actually it only starts repeating after goodness knows what, sort of 30 odd down these heavy weight, or these are just numbers. This is just ordering the by weight. And so that they're not really at the moment, don't have any significance. They're just, you know, the first, the second, the third, and the fourth in order of mass. And this proved to be a pretty successful system, particularly when, by the fact that when Mendeleev did it, he found that actually there must be some things that we hadn't discovered yet, because if he just put in everything that we knew of in the order of heaviness, the table sort of was out of step by 1 or 2 at the end. So he realized, we must have not, say, found osmium, because if I put a gap there and then shovel everything else along, it all matches up beautifully. So come on, you geologists, you need to go out and find me something, because we're missing 1 or 2. And the fact that that actually worked, and it was then discovered he could actually also, by comparing the ones above, say, and what's more, I reckon it's going to have a melting point of about this, and it's going to have a density of about that, and it's going to look a bit like this. And so that's what they found. And this was a pretty good example of science, if you like, the sort of technique where you induce a theory from what you've observed, and then you use it to predict something, and then you go and see if that prediction turns out to be right. And if it does, you think, oh, that's quite good, isn't it? Yes. So, right. So that was where one has got to with what are things made of. But at this point, of course, there's no direct evidence for atoms or molecules or anything. It just seems that's the most likely explanation for why things combine in nice integer numbers. And that, but it's only a proposal at this stage. Now, there was another line of attack. Oh, it's one thing I just did want to say, actually. I forgot to mention it, but I thought it was quite an interesting observation that from this table of elements, which but I'll just share that again, just to remind you. Yes, I think it's that, isn't it? We've still got. Can you all see the table of elements? So the I just wanted to mention that that oxygen here, oxygen is pretty close to the reactive end of the non-metals. So fluorine is more reactive, but oxygen is pretty close to it. So oxygen likes to form compounds with pretty well anything that it can. It loves to form compounds with metals, and it will grimly form a compound with nitrogen, carbon, phosphorus. It will form a compound with virtually anything. And therefore, it is the most incredibly unnatural thing to find just sloshing around in a planetary atmosphere. And this is why it's sort of seized on as something to look for if one is able to look for things in other planetary atmospheres, because there's absolutely no way you should end up with oxygen on its own. If there's anything around at all for it to react with, it'll do so. I think the red sands of Mars are thought to be mostly rust, basically, because of such oxygen as there was has reacted with the iron to make iron oxide. So it's striking in a way that we are living in a chemical freak, an atmosphere with 20% oxygen is the most extraordinarily unreal, unnatural, unchemical thing that you can think of. And luckily it is, because otherwise we wouldn't be here. But anyway, that's a little aside. Whilst we're on this, let's move on now to I don't know, I'm not going to work. Yes, okay. And that's just to show the periodic table again, but with different colors indicate this time when the things were discovered. So the dark red ones are antiquity to Middle Ages, if you can see that. So those were the things that were known from a pretty early time. Then the sort of purpley ones and no, I can't actually see, is that green? Bright green, okay. Those are the ones that were sort of discovered in this period we've been talking about, where people were hunting out elements. And you can see that they got quite a few of them. These noble gases, so-called, because they didn't react with anything, were jolly difficult to discover. In fact, how on earth people did, I've no idea. But somehow some clever chap did quite late on in the 1850s. So that's sort of indication of how the picture was gradually built up. But now we come on to another sort of, if you like, indirect evidence for atoms and molecules, which was the behaviour of gases. And these people were significant there. Robert Boyle, you notice, is quite back in the early days of the 1600s, but Jacques Charles and Daniel Bernoulli are later, and they were, all of them did experiments on gases to see how they behaved. And so what they did was basically they in a confined volume of gas, they tried squashing it and heating it and seeing what happened to it. And they found some quite simple little relationships. That Boyle's law was that the pressure of a gas and times the volume it occupies is constant. So in other words, if you increase the pressure, but if you double the pressure, you halve the volume that the gas occupies. If you halve the pressure, you double the volume that it occupies. So that was Boyle's effort. Charles saw what happens if you heated a gas up. What happened? He looked at it with constant pressure and looked at the volume that it occupied. And he did a sort of very common physics type approach to looking at that sort of thing. He plotted a graph. He heated it, he measured the volume at a particular temperature. We're going to have volume up here and temperature along there. Got a value, increased the temperature, got another one, increased another temperature, got another one, increased the temperature, got another one, and found that it was actually a beautiful straight line. There's a very nice little linear relationship. If you increase the temperature, you increase the volume, and the same increase in temperature causes the same increase in volume. And another set of experiments looking at pressure with variation with temperature proved to reveal the same thing. Again, that a given increase in temperature caused the same increase in pressure wherever you were. One interesting point emerging from this was, well, what happens if you extrapolate, as the expression goes, down to there? What temperature would you have if you actually didn't have any volume at all? And this turns out, so this led to the idea of a sort of absolute zero. If you did a similar graph of pressure and had a different straight line, that again, if drawn back to an imaginary point at which the pressure was absolutely nothing, in all cases, if it was done accurately, you got a value of about minus 273 degrees centigrade. That appears to be as cold as you can absolutely get. That is known as absolute zero, and physics temperatures are measured absolute from that point. So 15 degrees centigrade is actually 288 Kelvin on this absolute temperature scale, measured from the absolute bottom temperature you can possibly have, absolute zero. So that was one interesting phenomenon that emerged from these gas experiments. But another thing that was, I think, was more significant really, was that Monsieur Bernoulli, who I mentioned at the bottom of the list we had, really formulated a view of gases which started to explain this. He said that you could imagine a gas as consisting of a large number of little atoms rattling about furiously. And the pressure that they exert is caused by them smacking into the walls. That's what makes the pressure. As they rattle around, they bounce off the walls, and that gives rise to a force due to the law of momentum that we came across last time. So now this is a bit physicsy, this is a bit more challenging, but I think it's still quite interesting for you to see how these sort of things worked, because one realizes, thinking about it, well, actually we ought to be able to work out what the speed of these things might be, because pressure is force per unit area. Now, what's that going to depend on? Well, it's obviously going to be related to the number of these mysterious little atoms that we've got in a unit volume. So I'm going to put divided by volume. It's the sort of density of particles, if you like. The more you've got per unit volume, obviously the more they're going to be hitting the wall, so the bigger the pressure is going to be. It's also presumably going to be dependent on the velocity of these things, because the faster they're moving, the more often they're going to hit the walls. So that's going to affect the pressure. And then, now you may remember, says he, looking grimly at Matthew, if I can see him, but I can't, because I haven't done your test, of course, but you may remember the little expression that the impulse, which was the force times the time, is basically what changes the momentum of something. And by implication, therefore, if I do a bit of maths twiddling, divide both sides by the time, the force is, if you like, the momentum changes divided by time. When something smacks into a wall, it had a momentum of mv one way, and then it's got mv the other way. So the change in momentum is 2mv. So basically, I mean, I'm not going to bother about factors of 2. That's one of the great things about physics. After, don't worry about 2, 3, who cares about that? This is known as an order of magnitude calculation to give you a sort of rough idea. So basically, the force is called, you can work out the force by the number of collisions times the momentum that each of them, the change in momentum that occurs at each of them. So that gives us, so this is really giving us the number that are hitting per second, and each of them, the momentum change due to them going one way and then ending up going the other is this. So we have got the number of items per volume times the mass of them, and then we've got 2 of these, so that's v squared. And the interesting thing is that, of course, although we don't know what the mass of the wretched little particles are, we don't know how many of them we've got, we do know that the number that we've got times the mass of each of them is the mass of the whole gas, isn't it? So this is something you can actually measure. It's just the mass, the weight of the gas. And that's the volume, which you can measure. So that's meant to be a big V. That's the pressure that you can measure. So you can actually work out roughly what this velocity is. So this is something which is to do with a completely, at the moment, hypothetical little realm of tiny little things rattling around, which you can actually get a value for it from ordinary measurements that you can easily make in your little laboratory. And that comes out to be about 250 meters per second, 300 meters per second. So they're rattling around pretty fast. That's about 500, 600 miles an hour, which some people might recognize as being quite close to the speed of sound. And of course, it's not surprising really that since sound is transmitted through air, it presumably couldn't travel much faster than the things in the air are traveling anyway. So there's obviously a relationship between the two. So that's a little bit of sort of nifty physics. And the next key nifty little thing about this is that it shows, therefore, that P times the volume has something to do with NmV squared. Now, again, as the other thing that you may remember from last time was that this expression, a half mv squared, is what we call the kinetic energy of something that's moving. That was what was delivered by the force times the distance it acts through. And what's interesting is that this now looks like the energy of the gas, because it's the number of items times this mv squared thing, which is the kinetic energy. And since the experiments showed that the P and the V were basically dependent on the temperature of the gas, that was the, if you put all the 3 laws together, that's this what you get, that PV, pressure times volume, depends on the temperature. That suggests, therefore, that this mysterious heat, which Lavoisier thought was a fluid, in fact, a lot of people thought was some sort of stuff that flowed from object to object, and turns out to be, on this kinetic theory of gases, actually something rather more straightforward. It is the energy that the molecules have got as they rattle around. And this is consistent with what we were thinking before. If you compress a gas, you do work on it by your force moving through a certain distance, and that work done renders itself visible in the form of the increased energy that the gas has as a result. Heat, being a form of energy, therefore, or kinetic energy, sort of adds to this gradual discovery of the so-called law of conservation of energy, that actually you don't, just like mass, you don't create it or destroy it, you just transform it from one thing to another. The temperature is, therefore, is the average amount of energy that each little thing has got. Obviously, the total amount of, if you like, heat energy in a great big copper pan is going to be much bigger than the total amount of energy in a tiny little grain of salt. But if they're at the same temperature, it means that each of the atoms in the copper pan and each of the atoms in the sodium, of the salt, have all got the same amount of energy on average. Now, as things bash around to each other, some will be moving faster, some will be moving slower. But on average, the temperature is a measure of how much energy each thing that can have energy has got. And some gases are very simple. The only sort of energy any of the particles can have is just by virtue of them flying around. Other things, like water, which is some sort of, a water molecule is something like that. It can be doing lots of different motions. It can be vibrating, the hydrogens can be sort of rattling in and out, the things can be spinning round. It can do all sorts of different motions, and interestingly, the energy spreads itself out across all of them. So water, there are so many different ways each molecule can move, and therefore over which the energy can be distributed, that it takes a lot of heat to raise the temperature of water compared with other substances. Water is actually very hard to heat or cool, as those of you who still do washing up will know that if you've got a bowl of hot water, you can put a stack of plates into it and it cools down, but it doesn't cool down anything like as much as the plates warm up. That's just a consequence of the number of different degrees of freedom over which the heat energy is distributed in the case of water. So that's all pretty complicated stuff, isn't it? Right, but at any rate, I think where we've now got to is that this again was only a surmise. It again worked very nicely, assuming that a gas consisted of little tiny billiard balls rattling about. That explained what happened when you heat it up, why that makes the pressure go up, and why the pressure is dependent on the volume. But there's still no actual evidence. We don't know how big or small n is, or how big or small n is, but it seems to work as a theory. And that's where I'm going to leave the sort of physics bit today. And in the last sort of 5 mins, I will just ruminate again on the whole sort of question of science and measurements and theories, and, you know, our view of reality, etc. And there are 2 points I want to make emerging from some of this. First of all, the incredible amount of painstaking work that went into a lot of these discoveries. I think I mentioned last time that Newton's gravitational work was based on the calculation of the nature of the orbits of the planets around the sun. And that must have taken an incredible amount of work, because all that you could really do at any time is to measure the, I suppose if you've got the sun here and you've got the Earth and you've got Mars, all you can do is to, and then the stars are sort of out here, you can do lots of measurements of where Mars appears to be against the sky. And you can do those over and over again, night after night, year after year. And in this case, of course, people had been doing it for thousands of years. Ptolemy, a Greek, but this time I think he was 500 AD, but he had enough information to get quite good predictions of the way things were going to work in 500 AD. So by the time that other astronomers got really going in 1500 AD, they got 1,000 years worth of sort of observations behind them, and also predictions made 1,000 years ago, which they could see whether they still worked. And they didn't terribly well. And I suppose what you have to do, if you've got all these measurements, if you then sort of say, well, supposing the Earth goes like this and Mars goes like that, well, now the next one ought to look like this. Oh, it doesn't, it looks like that. Okay, well, maybe Mars went a bit further than that. And you go, oh, no, that doesn't work. Well, maybe we'll make Earth a bit further in there. You know, gosh, and on and on and on. And some people like Tycho Brahe very well spent their whole life, presumably, doing that sort of thing. Gosh, well, quite interesting, actually. I thought I was going to go into astronomy when after I'd done my physics course at university. I thought, yes, professional astronomy. But I think I realized that I wasn't actually motivated enough to do that sort of thing. A real scientist is happy just to do that. I thought I would just have grand theories, and realized that I wasn't actually probably clever enough to do that. And I didn't really feel like doing that, so I didn't go in for it. And the other area, of course, that we've come across today was this laborious business of mixing different proportion of things together and seeing what compounds come out and how much of them and how much this way and how much that way. Gosh, and again, Lavoisier spent ages doing it. He unfortunately was executed in the French Revolution because he was considered to have diddled his taxes or something. So he came to a rather sticky end. But at any rate, all very laborious. And I think that's one thing that's just interesting to consider, how much of the sort of advances that have been made are on the shoulders of people who ground away with very laborious and precise work, sort of, which allowed great minds like Newton and others to sort of come up with theories, but they just did a lot of hard work. The second rather interesting thing, I think, is that Ptolemy's idea, you see, was that because they thought that everything went round the Earth, which meant that actually, because they're really going around the sun, you get very strange movements appearing. What Ptolemy did was that he said, okay, well, let's say that, well, since everything has to go in perfect circles because it's the heavens, to get these observed movements, we say that the planet actually goes in a circle round a point whose center goes round here. And maybe you have to add another one like that to get it better. And then you start saying, well, actually, it's the, you know, we have various odd, funny little things that are off center by a certain amount, and it's the line from that to that that actually counts. But it was all very complicated, but he got something that worked quite well. the interesting thing I feel is that he, and I think his compatriots, didn't actually think that this was what it was actually doing. They thought, though, that this was a good way of predicting what it was going to do, which was useful for sort of navigation purposes or other matters. But what it was actually doing, well, we hardly knew, but this was a good sort of prediction method. And interestingly, even as late as 1900, a number of people, famous scientists, including Ernst Mach, who was the one who, people with any aviation background, I've heard people talk about Mach 1.5, meaning 1.5 times the speed of sound. It's, you know, a common unit for aircraft, and meaning the speed of sound. So Ernst Mach in 1900 claimed that nobody's ever seen atoms or molecules. They're not real, they're just a convenient mathematical construct, rather like these epicycles, to help us predict what's going to happen. But it's not actually like that. It's just a way for our simple little human beings to sort of predict behavior. And of course, subsequently, Einstein and others then began to come up with hard evidence of the actual size of molecules and the actual numbers of them. But we gradually, therefore, I feel, have sort of come to see all scientific theories as being not just ways of sort of calculating or predicting or forecasting, but actually giving us clear idea of what actually is happening, actual reality, if you like. And whereas in the early days, these views were very much seen in the realms of helping calculations. And interestingly, during the era of Lavoisier, there was a sort of clash there. I think a chap called Priestley in England, who was a very good chemist and was also a finder of elements, he refused to believe Lavoisier's view that when something is heated up and oxidizes, it's not that the oxygen in the atmosphere combines with the substance, and it's not that something comes out of the substance, that sort of heat or phlogiston or something comes out of it. And Priestley wouldn't accept this, and I didn't quite follow the little write-up in Wikipedia, but I think it was something along the lines that he was saying, well, it's all very well, all these measurements can be used to sort of help, if you like, understand measurements, but they don't help you understand what's really happening, which you have to get at from a sort of philosophical or thinking way. It's not by measurements, you know, you can just sort of do that to get a bit of a way of fixing the figures, but that doesn't really tell you what's happening. So there was a sort of clash, which gradually, as time wore on, we got much more into the way of thinking simplistically that anything we find that works like that is exactly how it is. So in other words, gases are little billiard balls rattling around, and the things that we'll discover next week are what light and sound are. And then, oh gosh, in the middle, well, really the early 1900s, it all started to go wrong again. Oh dear, because actually it didn't quite work like that, that maybe we couldn't quite work out what the things were. And I think as time has gone on up to this point in physics, we've got even more muddled about what on earth's going on. It really is weirder and weirder by the minute. So that's an interesting little sort of observation about sort of reality and theories. And you will be relieved to hear that is the end of that. So I shall stop the recording. Stop recording.